Today we move our focus to Chapter 2, Section 1, and we start talking about functions and their graphs. Now we've already emphasized the fact that we know we're familiar with quadratic functions, those second-degree polynomials. We know that their graphs are parabolas. Now we're going to talk about several different types of functions, starting with the definition of a relation. Now, a relation is a very general definition. Like quadrilateral in geometry encompasses anything with four sides, and then we can start get more specific and talk about parallelograms and rectangles and squares. A relation is our general definition for any set of ordered pairs, where the set of the first components is called the domain, and the set of second components is called the range. When we are graphing on our coordinate plane, our domain is our set of x values, and our range is our set of y values. The domain values, the x values, are our independent variables. It's the input. It's what we plug in. What we get out is the range, the set of y values. The range depends on the domain, so these are our set of dependent variables. It's the output. When we talk about the function value, we're talking about the range. We're talking about the value of the function at a specific x coordinate. So where is y? What is y at any specific x? The range, the y values, are dependent on the x values, and that's what we call our function value. We're going to create a relation from the graph that we're given and then identify the domain and range. We can decide if that relation is a function or not. Now you have this PDF, so I'm going to give you opportunity to go ahead and pause the video and read the information given and evaluate the graph. So if you read the information, you can see that we have basically a side-by-side bar graph with 4 of the least corrupt countries and 4 of the most corrupt countries. Now, the higher the score on the corruption rating, the less corrupt the country is. So these are our least corrupt countries with high scores, and these are our most corrupt countries with low scores. When I set up these ordered pairs for my relation, I'm comparing the country to their score. So for my least corrupt countries, I have Iceland coming in first. Unfortunately, I don't know abbreviations for most of these countries. I have Finland coming in just behind Iceland at 9.6 and tied with New Zealand. That one I know. And then there's Denmark at 9.5. So those are our top 4 least corrupt countries. When I look at our most corrupt countries, we've got Bangladesh and Chad tied, and I'm going to go ahead and abbreviate Bangladesh at a score of 1.7, and then we've got Chad also at 1.7, and then Haiti and Myanmar, sorry, tied at 1.8. So there is my set of ordered pairs. Now, these are not XY ordered pairs as stated. My domain is my set of input values, so that's the country. And my range is the set of output values, so that's their score on that corruption index. Is this relation also a function? Well, yes, because each of my domain values is different. Okay, let's look at the next one. Take a minute to look at this one, read the information given, and then set up the relation, the set of ordered pairs that are identified by this bar graph. Okay, so hopefully this is what you came up with. We only have 4 bars represented, so we only have 4 ordered pairs in our relation. This graph is a little different. So if you are 60 years old today, what is your percent chance of living to be, and then the ages are what we were given to live to be to age 70, age 80, age 90, age 100. And then the range, the output, is what percent chance you have of reaching that age. So if you're 60 years old today, you have a 86% chance of living to be 70, but you only have a 2.7% chance of living to be 100. Okay, so that's our introduction to the concept of ordered pairs and a relation with domain and range. Let's look at the next page. On the next page, we have a definition of function. A function is a more specific type of relation in which each element of the domain, or what is typically our x value, corresponds to exactly one element of the range, or to exactly one y value. If I have a function, no two ordered pairs will have the same first coordinate and different second coordinates. Are the relations that we created on the first page both functions? Yes, they were, because we did not have any repeat values for our domain, so we didn't have to worry about whether or not they were functions. Another way to check to see if a relation is a function, if we have a graph, is to use the vertical line test. The vertical line test states that if there's any vertical line that intersects a graph in more than one point, then the graph does not define y as a function of x. So we take our vertical line and we see, okay, well, you know what? The y-axis is a vertical line, and it goes through this graphed function in two places. So y is not a function of x for this first graph. What about the second one? I can take my y-axis, my vertical line, and I could slide it left or right, put it wherever I wanted to put it, and it's only ever going to cross in one place. That means that this is a function where y is a function of x. C is also a function. There's no place I could draw my vertical line that would cross in more than one place. Now D, that checking any possible vertical line is important, because the way D is sketched, here's my graph, it intersects this vertical line, my y-axis, in exactly one place. So if we just look at that vertical line, then yes, that would be a function, but that's not how we use the vertical line test. We check to make sure any vertical line would only cross in one place. If any vertical line can be drawn that crosses the graph in more than one place, then that is not a function. I want you to pause your video, use the vertical line test on those next 4 examples, and then come back to see if we got the same answer. Okay, so there are our other 4 examples. Hopefully you can see that we count it yes as a function where any vertical line will only cross the graph in one place. We count it no as not a function if we can draw at least one vertical line that crosses the graph in more than one place. If I don't have a graph, I can't use my vertical line test, but I can still determine whether or not a relation is a function. Now I'm told to do 2 different things here. First, I say whether or not it's a function, and then I give the domain and range. I have lists of ordered pairs. For this first relation, I have 4 ordered pairs listed, and I see that my x values are repeated. Well, anytime my x values are repeated, if they are assigned to a different y value, then that is not a function. Let's go ahead and list the domain and range, though, for this relation. When I have individual xy coordinate pairs listed, when I use my domain and range, I'm going to set it up in fancy braces, and I just list the individual values. For this relation, I have 3, 3, 4, 4 as my x values. I don't need to list each individual value more than one time. So my domain is 3, 4 in fancy braces, individual values. It's not a continuously drawn graph. These points would be just points on a graph, not connected. My next relation has 3 ordered pairs. And when I look at it, I see that each x value is different. If each x value is different, then it is a function. We're fine that that y value repeats. That's not an issue at all. What we're interested in is, does the x value, the independent variable, repeat? Oh, I'm sorry, I did not finish my range for this first relation. My range for the first relation is 4, 5, 4, 5, so I just list each of those values one time. Okay, let's do domain and range for the second relation that is a function. The domain for this function is 1, 2, 3. Again, individual points not connected, so I list them in fancy braces. My range is that single value 2, also listed in a fancy brace. We have a note down here that any relation that contains a y square does not define y as a function of x. Well, why is this the case? Let's look at x squared plus y squared equals 3. Now, I know, because I've been doing math for a long time, that if I were to graph this, this would be the graph of a circle. When anytime I have x squared plus y squared, I have a circle. But in general, we don't know that. So if I want to see if y is a function of x, I'm going to solve it for y. So if I want to solve this for y, I first need to move my x squared term to the other side. That gives me y squared equals 3 minus x squared. And then I need to finish solving for y. Well, how do I solve when I have a squared term, when I have that variable squared? I use my square root property. When I take the square root of both sides, because this is an unknown, I have to consider plus or minus. So what I get is that y is equal to plus or minus the square root of 3 minus x squared. Now, let's assume x is maybe 1. So 3 minus 1 is 2, and I've got the square root of 2, which does not simplify any further. But because of this plus or minus out here, if I plug in a single value for x, I get out 2 different answers for y. I get a positive square root of all of this, and I get a negative square root of all of this. So anytime I start with a y square, when I take the square root of that to solve for y, I get 2 different values. And when I have 2 different values assigned to the same x coordinate, to the same independent variable, that means I don't have a function. All right, let's look at the next page. On the next page, we see we have some function notation. Function notation just enforces our definition of y as our dependent variable as our function value. Y is defined as the value of the function at x. So y is the exact same thing as f of x for any x value in the domain of the function. That means that I can take out the y and replace it with my function notation f of x. When I write this equation, y equals 2x plus 3 in function terms, I have f of x equals 2x plus 3. And this implies to us and encourages us to recognize that we plug in a value for x, that's our input, and we get out the function value, which is the same thing as my y value or my output. So we are going to evaluate the function. This is the function that I've been given. If I want to evaluate the function for f of 5, that means I'm going to plug in 5 anywhere I have an x. Well, this is a pretty simple linear function. I only have one x value to replace. 2 times 5 is 10. 10 plus 3 is 13. And I've evaluated the function for that x value, 5. That means that if I were going to graph this, I would have the ordered pair 5, 13. 13 is the function value at the x coordinate 5. Let's look at the next one. F of negative 1 for this function would be 2 times negative 1 plus 3, or negative 2 plus 3, which is 1. And I have another ordered pair that falls on my graph, where x is negative 1, y is positive 1. Now this that I'm filling in here is a little less straightforward, because instead of just filling in a constant, I'm filling in an expression, x plus 2. But I still am substituting in for this x coordinate, this x value. So I have 2 times, this time, instead of just a single term, 2 times x plus 2, and then plus 3, because that's the rest of my function. I have to use my order of operations correctly and distribute this 2 inside the parentheses. That gives me 2x plus 4 plus 3, which is the same thing as 2x plus 7 when I combine like terms. Now I'm not going to write this as an ordered pair because it doesn't make sense. I don't have a specific value for x here. It would still give me an ordered pair for any value of x. It's just putting this function in different terms. It's creating an equivalent graph, an equivalent function. Okay, our next set of problems, we have 10 practice problems available. We are not going to do all 10. I'm just going to do the first couple with you, and then we will, if you would like, we can talk about those as a later date if you are struggling with this concept. But we're going to do, you know what, I think that we may do the odds. Let's go through and see how we do. For each graph, we are supposed to determine the function's domain and range, find the x and y intercepts, and the missing function value. So we have several things to do. The first thing we're told to do is find the function's domain and range. So for number 1, we have a parabola and we have arrows on the end. So that encourages us to recognize that we just have a piece of the parabola graph. It's going to keep going up and out forever. Because it keeps going up and out forever, it keeps getting wider and wider and wider. So when I talk about my domain, the possible x values that are included, I can pick any x value anywhere in my real number line and go up and find a function value that is assigned to that. My domain, therefore, is all real numbers, which I can write as negative infinity to positive infinity. I could write out the words all real numbers, or I could use my all real numbers symbol, which is like a fancy R with 2 downstrokes. My math lab does not use this symbol, but I use it for shorthand sometimes because it makes life a little quicker. So my domain is all real numbers. Another thing, I have a hard time with my infinity symbols. They end up with tails in the middle. That is not on purpose. I'm not trying to be fancy. They never meet correctly, very rarely meet correctly. So don't do the tails in the middle. An infinity symbol is basically a figure 8 on its side. All right, range. For my range, I'm looking at y values. I start at the least y value down here at negative infinity and I work my way up. So I see my function starts right here where my y value, my range value is -4, and it keeps going up forever. I know that because of the arrows. So my range has a lower boundary at -4 and it goes to positive infinity. My lower boundary at -4 is included, so that is a square bracket. I never get to positive or negative infinity, so those are always curved parentheses. Now let's talk about x-intercepts and y-intercepts next. My x-intercept is where my graph hits the x-axis. Whenever I have an x-intercept, the y value will be 0. This graph has 2 x-intercepts, or zeros of the function. I have an x-intercept at -3, 0, and an x-intercept at 1, 0. If it is a function, it will never have more than one y-intercept. A y-intercept happens where my x-coordinate is 0 because it's on the y-axis. So my y-intercept for this graph is 0, -3. The final thing I'm asked is to fill in the missing function values, and we have those questions down here. What is the function value where f is -2? So I go over and I find the -2 x-coordinate, and I go find that spot on my graph. Well, right there. F of -2 is -3. That's the function value at -2. My next one to answer is, what is the function value where x is +2? Well, where x is +2, I go up and find my function, and it looks like it's going to be up here at 5. I'm not quite there yet, so I'm going to say f of 2 is 5. All right, like I said, we are just going to go through some odds here. I'm going to give you the evens to do on your own. So let's look at the next one. Number 1 was a parabola. This one is a V-shaped graph. We're going to talk about this in a minute. A V-shaped graph is an absolute value function. First step is to find domain and range. Well, just like my previous graph, I have arrows on the end, which means my function, this is just a little piece of the graph. It just keeps going out and out and up. So if I work on my x-axis from least to greatest, from negative infinity to positive infinity, there is no x-coordinate that is not included in the graph of my function. So the domain of this function is, again, all real numbers, or negative infinity to positive infinity. My range, again, has a lower value, a least value. So I have a boundary down here that I'm going to start at. So as I travel up my y-axis, my function starts at this y value 1, and it just keeps going up forever. So it is from 1 to positive infinity, where 1 is inclusive. I never use a square bracket with infinity or negative infinity. Those are always parentheses. Now let's talk about x-coordinates or x-intercepts and y-intercepts. Because my graph sits with a vertex above the x-axis and it opens up, there are no x-intercepts. I'm not going to leave that blank. I'm going to say not applicable, or I could say none. Y-intercept. If it's a function, I only ever have one y-intercept. It always happens where x is 0. In this case, my y-intercept is 0, 1. And then finally, I need to find the function values that I'm asked for. The first one I'm asked for is f of negative 1. So I go over on my x-axis, because that's an x-coordinate, to negative 1, and I go up and I see that the y value for x is negative 1 is at 2. And then the other one I'm asked for is the function value where x is 3. So again, I go to my graph, I find x is 3, I travel up to see where it intercepts my function, and I find that y value is 4. We're going to go ahead and finish out the odds. So we will do 5, 7, and 9 on that next page before we talk about parent functions. On number 5, I do not have an arrow at either end of my graph, which means I'm going to have upper and lower boundaries for both domain and range. So let's look at this. Let's see domain and range. For domain, I'm using my x-axis. I start over here where x is small at negative infinity, and I travel just like I'm reading a book in a positive direction. And I see that my function starts right here where x is 0, and that this dot is filled in, so that value is included. So my function starts where x is 0, and it keeps going continuously until I get here where x is 5. And that is an open circle, so that is not included. My domain, therefore, is from 0 to 5, where 0 is included, square bracket, and 5 is not included, parentheses, because that is an open circle. That means the last x value I can plug into my function is going to be 4.999999999. It goes right up to, but does not include 5. Now let's talk about the range. For the range, I start at the bottom and I work my way up, because I'm moving from least to greatest up the y-axis for the range. Now, as I start working up the y-axis, I see that my function starts at the y value negative 1, and again, that boundary is included. I keep traveling up, and my function stops right here where y is 5, and that is not included. So my range is from negative 1 to 5, where negative 1 is included and 5 is not. Now let's look at x and y intercepts. My x-intercept happens where y is 0, and my y-intercept happens where x is 0. So my x-intercept happens where y is 0. My y-intercept happens where x is 0. My x-intercept, where y is 0, I run into the x-axis at 2. My y-intercept, where x is 0, I run into the y-axis at negative 1. And then I have to give the function value I'm asked for, f of 3. Well, when x is 3, my y value is 1. F of 3 is 1. Okay, let's do number 7. For number 7, I have another piece of a graph, but you see I do have an arrow this time. So this function is continuing out this direction. This is actually a square root function. We're going to talk about that in a minute. Let's do domain and range. As I move across from left to right, increasing on my x-axis, I see my domain starts at 0 inclusive, and it's going to keep going forever. So my domain is from 0 to positive infinity. As I move from bottom to top, least to greatest, up my y-axis, my range starts at 1. Now, it's moving out a lot faster than it's moving up, but it's going to keep moving up. So my range is from 1 to infinity, where 1 is included because, again, it's filled in circle. Let's look at x and y intercepts. X-intercept, y-intercept. My x-intercept happens where y is 0. And if I look at this, y is never 0. This graph, again, does not intersect my x-axis. So I have no x-intercept. I'm not going to leave it blank. I fill in NA for not applicable. My y-intercept happens where x is 0. I do have a y-intercept there at 0, 1. And finally, for this problem, what is f of 4? What's the function value of this graph where x is 4? Well, when x is 4, it looks like y is 3. One more for us to do together. This is a segment, not a line, on number 9. I know it's a segment because there are no arrows on the ends. They have boundaries, upper and lower boundaries. I want to encourage you to pause the video and try this one on your own and then come back to see how you did. Domain and range have my domain as I go from left to right. My boundaries are at -2 and 6, both included because they're both filled in circles. My range as I go from bottom to top goes from -2 to 6, but for different reasons. I'm moving in different directions. Then I look at x and y intercepts. X-intercepts happen where y is 0. Y-intercepts happen where x is 0. When y is 0, my x-intercept is over here at 4. And my y-intercept when x-intercept is 0 is up there at 4. Now, you see that my x-intercept is 4 and my y-intercept is 4. Those do not refer to the same points. That's why I emphasize putting things in ordered pairs. My math lab will usually let you give just the value. I like you to give ordered pairs so that I know that you know what you're talking about. And then finally, what's the value at f of -1? Well, where x is -1, my y value is 5. I'm going to ask you one more question on this one that is not given, but what if I said, what is f of x at 2? Well, in this case, I'm asking you for the x value. I've given you the y value. So in this case, you're going to say, all right, I know y is 2. Well, when y is 2, I'm up here, and that is this point where my x coordinate is also 2. So if I were to give you f of x equals 2, you would say that happens when x is 2 for this graph. All right, we are not going to do the evens together. I'm going to leave those. Let's look at this last parent functions and symmetry page. This is a good introduction to how we focus on types of functions for college algebra. Instead of calculating a lot of individual points, we're going to focus on translating functions and moving the parent function, because it retains its basic shape, around on the graph. Now, this page tells you each type of function has a specific shape for its graph. That shape is maintained for that function type no matter what you do to the equation. The most basic function is called the parent function, and then everything we do to it keeps it part of that family of functions. The parent function undergoes transformations in the form of shifts, flips, and stretches, but it is still the expected shape. For example, f of x equals x is my parent linear function. Anytime I see a graph that is f of x equals x where I don't have any other exponent, it's just x to the first, When I graph that, the graph is going to be a line. Now this is the parent function. It's a line with a positive slope of 1. It goes through the origin. But I could take that line, shift it up or down, make it more steep or less steep. It's still a line if my equation just has x, not x squared, x cubed, square root of, anything like that. It's going to be a line. Then we have our absolute value function, where we have x in the absolute value bars. Anytime you have an absolute value function, that is going to be a V shape. Transversely, if you have a graph and the shape of the graph is a V, you know your function is absolute value. Anytime you see a parabola, you have an x squared function, which is a quadratic function. We already talked about those. Then on this next line, we have f of x equals x cubed. This is the basic shape of my cubic function. And I'm going to skip over one, and you see I've got this kind of backwards S shape laid down. That's the inverse of my cubic function. The inverse of my cubic function is the cube root function. If I took my quadratic function and flipped it across and laid it over, it would be a u, or a parabola on its side. Well, that wouldn't be a function. So to define it as a function and do my square root function, I just consider half of the parabola, the positive half, instead of plus or minus. I just do the plus, the positive half. Now, these are the 6 basic parent functions that we're going to focus on in this unit. Later on this semester, we're going to get to these last 3. I will go ahead and name them for you. We have a rational function. Rational functions have an x in the denominator. We have an exponential function. Oops, I can't spell today. Exponential function, where our x is in the exponent. And we have what we call a logarithmic function, which is the inverse or the flip over of our exponential function. Again, we're going to get to these 3 later, not this unit. At the bottom of this page, we talk a little bit about even and odd functions. An even function has symmetry about the y-axis. For example, if I plug in a negative x, I get out the exact same value. An example of an even function would be my parent absolute value function, because if I plug in a negative x and I take the absolute value of negative x, I get out a positive x, just like I would get out a positive x here. It's symmetric about the y-axis. I could fold this graph on the y-axis and both sides would match. My parent quadratic function is also an even function. F of negative x, if I plug that in and square it, nothing changes. I still get out what I got before when I just plugged in positive x. I could fold this graph on the y-axis and the sides would match up. Nothing changes. These are both examples of even functions. Whether a function is even or odd helps us with the graph. As our graphs get more complex later on, it helps us to see what the graph is going to do. My primary simple example for an odd function is my cubic function. An odd function is symmetric about the origin. If I plug in a negative x, I get out the opposite of the original function value. So right here, my odd function, if I plug in a negative x, I get out the opposite of what I got before. So let's look at our cubic function. If I took f of negative x and I plug that in and cube it, a negative times a negative times a negative is still negative. I get out a negative x cubed. That's the opposite of what I got when I plugged in positive x. I get out a negative x cubed instead of a positive x cubed. This is an odd function as the parent function. It's centered on the origin and it's symmetric about the origin. It has that kind of a twist in the middle. This right side is up and the left side is down. So you can think about reflecting it over the y-axis and then reflecting it down over the x-axis. You can think about it as having a twist in the middle. But odd functions are symmetric about the origin. Even functions are symmetric about the y-axis. Now, these parent functions are odd or even. If I took my quadratic function and I shifted it over to the right, it would no longer be symmetric about the y-axis. It would no longer be an even function. If I took my cubic function and I shifted it, say, up and to the left, well, then this turning point, this vertex, is no longer at the origin, so it's no longer an odd function. But we can talk about those generalities just to introduce them now. We'll look at them more when we get to the next section.